Welcome. In the previous weeks, we have studied key concepts of evolution, namely natural selection, adaptation, and fitness. This week, we're going to study foraging behavior using those key concepts of evolution. First, we are going to study the foraging behavior of the northwestern crows. Then we go to the optimal foraging theory. Then we turn to social foraging. Why do animals sometimes forage together? Next, we turn to humans, spice use in humans, where we try to understand what Darwinian puzzle is. Lastly, we're going to talk about discussion questions. Before you proceed any further, I want you to watch this video. Go to this web page and watch this video. In this video, you watch the Japanese crows. They drop nuts from some height for breaking, and it is the Japanese crows have developed some ingenious way to break nuts easily and safely. Their cousin, northwestern crows in USA, they exhibit some similar behavior called the shell-dropping behavior. They go to the beach and they search for some whelks in the intertidal zone. Once they find some suitable whelk, they carry it to the land and they drop it from height for breaking like this. And this dropping behavior is repeated over and over again until the whelk breaks. And Dr. Reto Zach observes the foraging behavior of these northwestern crows, and this is what he found. The northwestern crows consistently drop a whelk from a mean height of about 5 meters. It's 5 meters, and the crows appear to be selective. They pick up only the large-sized whelks, not the medium-sized, not smaller ones. Only they chose large-sized whelk. They are also persistent. For instance, one crow was observed to drop a single whelk 20 times. From this observation, he raised these questions. Do crows drop whelk from the best height for breaking? Whether this 5 meter is the best for crows? Second, why do crows select only large whelk for dropping? And third, why do crows not give up and search for a new whelk if a particular one does not break readily? Let's think about this whelk dropping behavior for a minute. If you drop a whelk from a lesser height, for example, like 2 or 3 meters, you may save energy to fly up, but it may not break easily. If you drop a whelk from a greater height, it may increase the probability of a breaking whelk, but you have to spend energy to fly up. So you'd guess that there must be some optimal height where you break whelks while minimizing the energy to fly up. So Dr. Zack did some whelk dropping experiments. He set up a pole, a 50-meter pole in the sand, and he chose 3 kinds of whelks: small, medium-sized, and large whelks, and he dropped them at different heights. And this is what he found. The x-axis, that's the height of drop. It's 5 meters, 9 meters like this. And the y-axis, that's the number of drops per whelk. So each curve, that's the average number of drops needed to break a shell. For this yellow one or orange one, that's for the large whelks. This green one, that's for the medium whelks. And the purple one, that's for small whelks. So this is the way you read this graph. If you chose the large whelks here, and you drop that at 3 meter height, then go here, and 3, it required around maybe 13 times to break. If you choose a medium-sized whelk, and you dropped it from a 5-meter height, you go here, and it may be around, you have to drop 12 times to break. So at any given height, just look at this. There is no overlapping between the curves. So the curve for the large whelk is below the other two, and the curve for the medium whelk is in the middle, and the curve for small whelks are above the other two. So at any given height, the large whelks are required of fewer drops than the medium-sized and small whelks. So large whelks broke much more readily than medium and small ones, and they required fewer drops for breaking at all heights. So this is Zack's finding. The probability that a large whelk would break improved sharply at the height of the drop increased up to 5 meters, but going higher, like a 7 or 9 meters, did little to improve the breakage rate. The large whelks required significantly fewer 5-meter drops before they broke than either the medium-sized or small whelks. And third, the chance that a large whelk could break was not affected by the number of previous drops and was instead always about 1 chance in 4 at any given drop. Now we go to the optimal foraging theory. Do you remember that the northwestern crows, they chose only the large whelk, not the medium-sized, small ones? And why they chose the large whelks only? If you understand this question, we have to know the energetics of foraging. Energetics, you study the energy required to open a whelk, also to study the energy content for a whelk. So if you, the energy content of the large whelk is about 2.0 kilocalories. It is about 0.6 calories for medium whelk, and so 0.1 kilocalories for small whelk. But if you want to open a whelk, it means that you fly to the beach, pick up a whelk, bring back to the sand, and you drop from a height, and you do this behavior until you break it. All this required is you calculate the energy for all these behaviors. Then you have to spend about 0.5 kilocalories to open a large whelk on average. And you have to spend 0.9 kilocalories for medium-sized whelk. You have to spend 1.4 kilocalories for small whelks. So net gain, that's basically you subtract the second row from the first row. You will get about 1.5 kilocalories for large whelks. That's good. But look at this here. You get minus 0.3 calories for medium whelk. Basically, you spend more than you get. It's even worse for the small whelks. It means that you have to choose only the large whelks. Even if there are plenty of the medium-sized whelk, then you should give up those area, then search for the another area for the large whelks. Crows have many decisions to make while foraging. Where should we search for food? At what times of day? For what prey? How long should it spend trying to process the prey that it has found? And when to change the foraging site? But from the example we just studied, they chose to drop whelk from about a 5-meter height, and they only select the large whelk for dropping. And what does it mean here? These two behaviors? These two behaviors, it yields the most calories while expending the least amount of time and energy possible in doing so. And optimal foraging theory states that the organisms forage in such a way as to maximize the energy intake per unit time. Again, that's the energy intake per unit time. In that sense, the northwestern crows is an optimal forager. Now, We turn to social foraging. Why do animals forage together sometimes? This is a picture of pigeons foraging together. You often watch these pigeons foraging together in a park. We have just learned that the animals should forage efficiently, but it's no good if you are caught by a predator while foraging. And there's lots of predators love to catch pigeons, and one of them is the goshawk. That's a bird of prey. They love to prey on pigeons. So what's a foraging strategy for pigeons? First, they have to maximize food intake. We have just learned before, like in optimal foraging theory. But at the second time, you have to minimize predation risk while foraging. Then how do you minimize the foraging risk? First, you avoid the time and location that are the most dangerous. It means that you should meet there where your predators are. And you should forage in groups and spend time looking for predators. Let's study this second point here. The pigeons, they sometimes forage together in groups. And how is it different from foraging alone? That's the foraging alone here. And that the y-axis, that's the successful hawk attacks. If you look at here, then the chances are, if you forage alone, you are caught by a predator 80% of the time. If you're foraging together in a group of 2 to 10, you are caught by a predator about 50% of the time. If you forage in a group of 11 to 50, then the chance is down to about 10%. It's even better if you forage in a group 50 or more. So there is a decreasing attack success with increasing flock size. So if you're in a big group, you might be safer. And let's study the attack success and response distance. What is the response distance? That's basically when the pigeon realizes the predator is coming. So if you know when the predator is coming, if you detect the predator is coming at a greater distance, you have more time to respond. So if you respond, if you found the predator about like 20 meters away, then that's the chances of you getting caught by a predator about less than 10%. But if you just realize that the predator is right around you, 0 meters, then the chances of being caught by a predator is about 50%. So what it means is that if you detect the prey at a greater distance, your chance of survival is better. So let's combine these two studies together. Here's the graph it's not really good, but here's like open circles and solid circles here. The open circles indicates unsuccessful attacks, and the solid circle means kill, you are dead. If you're in a group 50 or more, look at the response distance. It's usually better than 20 meters or greater. There's a one, it's less than 20 meters and it's dead. But the chances are, if you're in a group of 50 or more, they detected the prey earlier at more than the 20 meters distance, and most of them survived. If you're in a group of 10 or 50, it's still good. Some of them died at less than 20 meters, but most of them survived. If you're in a group of 2 to 10, now you start to see more pigeons died here because your response distance is now down to less than 20. But if you forage alone, most of them dead here. Only the two survived. So as flock size increase, the pigeons detected an approaching bird at a greater distance. So the many animals, they group together to avoid predations. The grouping increases chances of predator will be spotted before it can successfully attack. So grouping also increases time spent foraging, and individuals have to scan less often in a group. It's basically, while foraging, your heads are down looking for food. But if you want to detect a prey coming, you have to raise your heads up and looking for the prey. You spend more time, if your heads are down and spend more time down there, then you can get more food, but you are susceptible to the attack by your predators. If you are in a group, in a big group, then some of their heads are always up looking for prey, so you are safer there. That's why you will see a herd of sheep, a flock of birds, a school of fish. Now we turn to humans, spice use in humans, where we study the Darwinian puzzle. We take it for granted to use a spice in our recipes, but let's think about it for a while. It's very strange to use spices because spices have very little caloric and nutritive values. Means that there's almost no nutrition in spices, but at the same time they are very expensive, especially in old times. So most of the major voyages of the early European explorers, they were motivated by the desires for spices. They spent a lot of monies looking for the spices all over the world. And so the spices, even if they have almost no nutritive value at all, people spend tons of money to buy them. So it seems to be it's a trait that appears to reduce the fitness of the individuals that possess it, meaning that we pay a lot of money when there is nothing valuable for us. So it reduces our fitness. So if the spice is the trait that appears to reduce the fitness of the individual that possess it, then it might be simply an arbitrary product of cultural evolution. That's the non-adaptive explanation of spice use. And Jennifer Billing and Paul Sherman of Cornell University, they brought up some adaptationist approach for the spice use in humans. So what they did was that some adaptive value of the microbes, the adaptive value of the spice. So they apply the spices where the bacteria are. So and this is the result. The spices, when you apply like garlics and onions and allspice and oregano, these spices almost kill and inhibit the growth of of almost all bacterial types. And up to here, all these spices, they inhibit the growth of more than 75% of bacterial types. And here, up to here, they inhibited the growth of half of the all bacterial types. So it seems to be that the spices, even if there is no nutritive value in it, they inhibit the growth of bacteria. And that's the adaptive function, adaptive value of the spice. So the Billing and Sherman brought up this idea, the adaptive value for the spice used in humans. If that hypothesis is right, then the risk of dangerous microbial contamination, the people should use the spice most often where the risk of the dangerous microbial contamination is highest. That's the tropical areas here. That's because they have the high temperature and humidity. So what they did was that they compared the traditional recipes at the low latitude and high latitude. And what they found was that the traditional recipes in tropical countries call for more the bactericidal spices than the recipes in countries in high latitude. If the adaptation approach for spice use is right, then you should also use more spice for the meat rather than vegetables, because the meats are vulnerable to microbial contaminations. And in a sample of cookbooks from 36 countries, the recipes devised for meat-containing dishes, they call for more the antimicrobial spices than the vegetable dishes. So it seems to be that the spices may have been used adaptively by humans. It means that they use spices to kill or inhibit the bacteria in human recipes. Now we're going to talk about the discussion questions. First of all, the discussion question 1. And we studied the whelk-dropping behavior of the northwestern crows. It's a cousin, the American crows. They also drop walnuts to break open, but they do behave differently here. These crows reduce the height from which they drop walnuts from about 3 meters on the first drop to about 1.5 meters on the fifth drop. And just think about why they do this behavior. They change the height each time they progress. Progress this not dropping behavior. That's the first question. In the second question, there's other math involved. Basically, what you have to do is that if the badger's ultimate goal is to maximize its rate of calorie gain, this is the optimal foraging theory states this. Should it forage for squirrels, scorpions, or both? So what you need to do is that you calculate the calories, the energy intake, the calorie intake per unit time. So to calculate the energy intake per unit time for squirrels and scorpions, and compare these two, and decide the badgers which one should forage. We have studied several examples of animal foraging behavior, especially the animals are the optimal foragers. They try to be efficient foragers. That way they increase their foraging success and their fitness. See you next week.